If you've ever driven past an oil refinery on the freeway, it's very likely you've seen a distillation column. These distillation columns are very high, they can be tens of meters high, and they're a series of plates. And the way distillation works is it relies on the differences in volatility of individual species that make up a mixture or solution. And to give an example, if we examine air and you wanted to somehow separate oxygen from air, we could design a distillation column such that the separation will rely on oxygen having a different boiling point than, or dew point than nitrogen and the other component, or carbon dioxide. And in the field of oil refining, distillation is how we extract different grades of fuel. So everything from the highest jet grade fuel to asphalt. And to draw a generic distillation column, what we'll do is we'll look at a series of trays. And we will have a feed stream. And in this example, I will discuss binary distillation because it is a good introduction to keep things simple. And so our binary means we are working with a two-component feed, and we will examine only the more volatile component, in which case I will define feed with a flow rate, total molar flow rate of F, and a molar composition of our more volatile component Z. And our feed will enter some tray, and coming down the column, we will have some liquid with a molar flow rate L, and below the feed stage we will have a new liquid flow rate. We may have a new liquid flow rate L bar, and coming up the distillation column we will have a vapor rising, and below our feed stage we call it V bar, and above the feed stage we call it just normal V. And at the top, so we can have more trays above and below, and your feed can also be the very bottom tray or stage. But at the very top of our distillation column, what we have is a condenser. And from the condenser, we will extract a distillate called D, and the distillate will have some molar composition of your more volatile component X sub D. And we will also send back down our distillation column some liquid with a molar flow rate of L, and entering our condenser. So I'll just write this out. This is a condenser. We extract heat from our system, QC. And at the very bottom of our distillation column, we have a reboiler. So this will be the reboiler, and in the reboiler we add in heat to our system at a rate QR, and we extract a stream with a molar flow rate capital B, moles per second, with a molar composition of our more volatile component denoted X sub B, and we send some vapor phase back up our distillation column, and that will have a flow rate of V bar. And at this point, I would like to note how our distillation column that we have just drawn is powered entirely by the heat that we are adding in to our reboiler, as well as extracting in our condenser. So if we wanted to double our molar flow rate, if we wanted to double the amount of solution that we could process, and we wanted to double the distillate molar flow rate as well as the bottom's molar flow rate, it's directly proportional to the amount of energy that we have to supply into and take out of our system. So we would also have to double QR, the energy that we're adding into our reboiler, as well as double the energy we take out at our condenser. And another thing, important note, is the mass balances that we can write on our system. And so if we do a total mass balance, we learn that if we draw our system boundaries around the entire distillation column, we will recognize that assuming there's no reactions, the number of moles are conserved, the feed total molar flow rate must be equivalent to the distillate molar flow rate plus the bottom's molar flow rate. So this is an important equation to remember. And if we do a component mass balance, what we will learn is that if we examine the number of moles of our more volatile component that enter our system must be equivalent to that leaving the system, we will have F times Z must be equal to D, the distillate flow rate, times the distillate composition XD, plus the bottom's molar flow rate times the bottom's composition of your more volatile component. So these two mass balance equations come in handy when we are working with distillation columns. And so that gets us two equations that we can use when we are trying to evaluate things such as the number of trays we'll need or other variables like that. Now in practice, if we wanted to figure out where we wanted to put our feed, so if we had a distillation column with a dozen trays, for example, if we wanted to know the optimal location to put our feed tray to maximize the efficiency of our distillation column, or if we were curious in figuring out how many trays we're going to need to order to make a distillation column with our specific requirements for the purity of our distillate stream that we need, what we will turn to is the McCabe Thiele diagram. So just to write out the motivation for this question would be where to put the feed, so which tray to put the feed at. And another question we would ask is how many trays are needed. So these are excellent questions that can be answered by the McCabe Thiele diagrams. Sorry, this pen doesn't register too well, but what I will do now is draw out a McCabe Thiele diagram, but first I will talk about the variables that we need to define before doing that. So the variables that play in a McCabe Thiele diagram will be the distillate composition, or the required distillate composition of your more volatile component XD, the molar composition of your more volatile component in your bottoms stream XB, the molar ratio of your more volatile component in your feed stream called Z, the quality of your feed, which I will go into, as well as two terms called the reflux ratio, which I call R, as well as the boil-up ratio, which I call VB. So this is reflux ratio and your boil-up ratio. And so if we wanted to figure out what the quality of our feed stream is, the way we will do that is if we are working at a system that is between its dew and bubble point temperature, i.e. it's not a supercritical fluid that hasn't been heated above its boiling point or cooled beneath its freezing point, what we can say is that quality is equivalent to the liquid mole fraction of the feed. And that is to say, if we had, if our feed was entirely liquid, our quality would be 1, so 100%. if our feed was entirely vapor, our feed would be 0. And to draw this out, to maybe make a little bit more sense, what we would do is if we were looking at our feed, within our feed tray, we will have some liquid from the top half coming down. We would have some vapor going up our top half. We would have some liquid descending the bottom half, and we would have some vapor ascending the bottom half as well, V bar. And our feed, depending on whether it's entirely liquid or entirely vapor or a mixture of the two, will either contribute to the vapor going up or the liquid coming down the column. To put that into words, what we would have is quality is equal to L bar minus L over F. So the liquid mole fraction going down the tray minus the liquid mole fraction that came down from the top half of the tray divided by the feed. And if we ask ourselves, does this make intuitive sense based on this kind of heuristic rule we have above? So if Q equals 1, if all of our feed is liquid, that will tell us that L bar will be equal to L plus F. So all of the feed will combine with the downcoming liquid, and if we substitute this into our equation for quality, this is the result we will get. If Q is equal to 0, if none of our feed was liquid, what we would find is that L bar would equal L, and so we will get 0 in the numerator and quality would equal 0. So that makes intuitive sense. The next term that we will analyze or evaluate before turning to a McCabe Thiele diagram is our reflux ratio. And our reflux ratio is equivalent to L over D, which is, in words, how much of the moles in our condenser do we send back down divided by how much we extract. And so in the case when R equals 0, when we have no reflux, this should make intuitive sense because we are not sending anything back down our column. And when R is equal to infinity, that means we are taking out, we are not extracting anything. And then finally, we have a boil-up ratio term VB, and this is equivalent to V bar over B, which again in words is very similar to the reflux ratio. It's how much we send back up divided by how much we extract in our bottom stream. So if VB is equal to 0, we're not sending any moles from our reboiler back up our distillation column. And if VB is equal to infinity, we are going to be extracting the maximum amount. Actually, I'm sorry. If it's equal to infinity, our denominator will approach 0, which means we are not extracting anything. And so now that we have defined our reflux ratio, our boil-up ratio, and our quality, and we also know the mole compositions in our distillate, feed, and bottom streams, we can now make a McCabe Thiele diagram. And the McCabe Thiele diagram looks something like this. So we will have an equilibrium curve that looks a bit like this. We will have an operating line that is simply a diagonal, and it's a straight line. And on our curve, we will have 3 points on our x-axis. The first point here corresponds to our bottoms stream composition. The middle point here will correspond to our feed composition of our more volatile component, and this rightmost x-coordinate will correspond to the distillate composition or molar ratio of our more volatile component. And on our McCabe Thiele diagram, we will have typically 3 lines. We'll have 3 lines. And this line is called our Q line, or a quality line. And the quality line will have a slope of Q divided by Q minus 1 quantity. So knowing the quality of our feed, we can determine this because we know that this point on our diagonal will have coordinates of z comma z. So for x and y, or xa and ya, so this axis is xa, we will know a point and we will know the slope. Therefore, algebraically and geometrically, we can find the equation for that line. The top line that we can draw on McCabe Thiele diagrams is called a rectifying line. And it represents the top half of the trays above our distillation column. And the rectifying line will have a slope of R divided by R plus 1 quantity, as well as a point of XD, XD. And at this point, I would like to note how if we were able to define the Q line as well as the rectifying line, we will be able to now figure out the third line, which is called the stripping line, is now fully defined. And so it's common in chemical engineering classes, you will be given just enough information to define 2 of these 3 lines. And so geometrically or graphically, we will be able to evaluate the third. And this stripping line corresponds to the bottom half, or the trays below our feed tray. And it will have a slope of the boil-up ratio plus 1 divided by the boil-up ratio, so VB, and this is equal to the slope, as well as a point of XB, XB. So if we were plotting this in MATLAB, we would plot a diagonal, our equilibrium curve, and these coordinates. And a common question you'll be asked to solve using McCabe Thiele diagrams would be how many trays will be required given a certain number of constraints. And the way we will do that, how many trays are needed, the way we do that, and I will redraw a generic McCabe Thiele diagram to solve this, is like so. So we'll have a diagonal, we'll have our equilibrium curve, we will have our coordinates corresponding to the bottoms stream, the feed composition, and the distillate composition, and we will have our 3 lines that will look something like this. The way we will evaluate how many trays are needed is by stepping up the McCabe Thiele diagram like so. So we will start here, and this will be our inlet tray or our bottom tray. We will hit our equilibrium curve, and then we will travel over to the right. We will go up again, hit our equilibrium curve, travel over to the left, go up again, hit our equilibrium curve, and then travel back over to the right. And so what this tells us is every time we touch our equilibrium curve, every time we need to reach equilibrium, that's an additional tray needed. So this will be the bottom tray, this will be the second tray, and this will be the third tray. So in this generic diagram that I've drawn, you would need 3 trays. And question as to where the feed tray should go. We look at where we switch our operating lines. And so what I mean by that is we notice how at tray 1 will be entirely on our stripping line, which is an operating line. I'll call it number 1. And then when we switch onto our rectifying line, where we make this step, which is at tray 2, is where we should put our feed. And this is the basics behind McCabe Thiele diagrams and binary distillation. I hope you guys find this useful, and let me know if you have any questions. Thank you for watching.